and good evening. Welcome to Kopernik Observatory. It's great to see you here on a dark and stormy night, or so what's soon to be a dark and stormy night. And also welcome those that are watching on the live stream. My name is Drew Desker. I'm the director here, and we're very fortunate that we've got just a great pool of resources that we can draw from to present here to the public. Let's see, a bunch of faces here are fairly familiar to me. Those in the back there, are you? Is this your first time up here? Are you, you've been here before? All right, great. It's great. Excellent, excellent. Well, so then I don't really have to explain what Kopernik is about. Often, especially for the first timers, I'll tell a little bit of background about what Kopernik is and what we do. But seeing how you know that, let's press on. Again, I think a lot of people think of Kopernik as just this 3 telescopes on the top of a hill, but we really do much more than that. And it's really an opportunity for us to understand a little bit more about how the world works, and either through our Friday night programs or our programs for kids. We may not necessarily turn every kid into a scientist or an engineer, but ultimately, if we can walk away learning a little more than we did when we walked in the door, then we've accomplished our goal. So tonight, we're actually have a program on a topic that's particularly of interest to me. I'm a huge proponent of renewable energy, and but I know there's a lot more to renewable energies than just the solar panels that are sitting on my house or here at Kopernik. And so we're very fortunate again to have Nikhil Karkhanis, who works with Siemens Energy, and he's here to talk about what it's going to take to get us to a net zero carbon world. So we're going to turn the camera briefly on you. Can wave to the public. All right, thank you much. All right, at this point, we'll let you. We'll take it from there.
Okay. Well, thanks, Drew. Thanks for giving me the opportunity to come speak here today. I hope everyone can hear me in the back. Yep. So I'm Nikhil Karkhanis. I am a mechanical engineer by profession. I've been working in the energy industry for a while, specifically in the power generation side of things. So I'm really quite excited to present this topic, which I feel like is very relevant for today, in today's world. So yeah, let's get started. So before I get into the talk itself, I like to start with some trivia. I'll show you some pictures like these. Can you tell me what these are? What systems these represent? Exactly. It looks like you really follow the trends in the energy industry. Yeah, for I guess folks who didn't hear that, that is a energy storage mechanism, and I'll provide some more details on that later. How about this one? Yes? Yes, you're right. That's a carbon capture mechanism or device. Good. How about this one? This is relatively easy, I would say.
Well, solar panels are reflecting right up to the tower with a piece of water.
Yes, yes. That's right. That's a tower for a concentrated solar power plant. So I'll explain these a little more in detail later in the talk, but I just wanted to start with this. So let's move on. So I guess the topic for today is net zero or net zero carbon. So what does that really mean, and why do we care about it? So everyone is familiar with global warming. What it is over period of hundreds of years, humans through their various activities have put out a lot of carbon dioxide in the Earth's atmosphere, and all of this carbon dioxide helps trap heat in the atmosphere and just warms up the Earth. So we are getting to pretty alarming levels today, where you see significant increases in the average global temperature above the pre-industrial period, and this, as we are already experiencing, can have catastrophic effects on our planet. So, so what is net zero about? It's essentially it's the balance of the amount of carbon dioxide you put in the atmosphere, balancing that with an equal amount that you absorb back, so that in the net you're not adding any more carbon dioxide to the Earth's atmosphere. So this is really the goal, and the focus of this topic, as far as what are the things we need to do to really get to a net zero state. So here's just some information from the World Meteorological Office, where they're showing the measured CO2 in the Earth's atmosphere, and you see it's pretty much a linear increase in CO2 since the 1980s. So just more information on the global warming aspect of things. So now I'd like to briefly talk about some of the policies or targets that are being discussed around the world now. You've probably heard of the Paris Climate Accord. Countries got together and they agreed that they're going to take action to limit the temperature rise, to 1.5 to 2 C from pre-industrial levels. So based on that, a lot of countries, governments are announcing their own measures so that they can actually meet this target. So in the US we have recent targets set by the president that we want to be net zero by 2050. Here in New York we have the CLCPA Act, which has its own targets: 85% reduction in greenhouse gas emissions by 2050, 100% zero emission electricity by 2040. So what I really want to stress here is that we have taken the first steps in terms of setting ourselves targets, and that's a good thing. Now the ball is really in the court of technology developers, manufacturers of equipment, to figure out how do we actually get there. And that's really going to be the focus of my talk, that what is the technology that is needed and what's being developed. And by the way, one relevant comment here is that starting next week there's a United Nations climate summit that's starting, where again a lot of the world leaders are going to come together, and I'm expecting to hear more hard targets set by countries, more announcements to come. So just something to keep an eye on. Okay, so now carbon emissions and energy use, they really are very closely tied together. So when we talk about managing our carbon emissions, we have to talk about how do we manage our energy use. And so this falls under the broad category of energy management. Now you could break it down into two sectors essentially. A sector where energy is produced, something like a power generation sector, and then somewhere where energy is consumed, like like we call this demand side management. So this could be something like, folks adjusting their thermostats at home. That's part of demand side management. Now, both topics are equally important in effectively managing our energy use. But for today, I'm going to focus on the energy production side, power generation side, partly because it's also some of my background, so I can provide more detail on that. So moving on. So I think when we talk about an energy transition, we need to take some of the historical perspective in mind as far as with regards to power generation, where did we start and how far have we come in terms of our technology. So I'd like to just show this briefly where, this graph is showing the main fuel sources that have been used, it's in the 1970s for our power generation plants. So as you might expect, coal has been the predominant source of fuel, until very recently. Until the 2015s, it was actually the most predominant. And then you'll see natural gas starting to pick up, in the late 90s to early 2000s. Natural gas and coal, these being the most carbon emitting fuels. I'll focus some of my talk on these two first, and then we can move into some of the others. So now some of the key drivers, behind transitioning of fuel sources are power plant efficiency. So power plant efficiency is, it's directly related to your carbon dioxide emissions. So I'll kind of go through, what have the developments been so far on in each of these categories in terms of improving efficiencies of our power plants.
If I could just ask one question, I'm just looking at your slide. I'm looking at the green bar or the green line for wind energy, and it seems like it didn't start collecting data until the late 90s, or that it really didn't become even viable until the late 90s.
Yeah, that's a good question, and that's something that I didn't notice before, but perhaps just the scale of this chart, where it's in billion megawatt hours,
right.
The amount of wind energy was significantly lowered, so that it's almost
was off scale.
It's off scale,
right.
Yeah.
Okay, thank you.
Yep. Yeah, that's a good question. Okay, so coal power plants. Coal power plants essentially use the steam turbine cycle. Now, in very basic terms, the cycle essentially involves taking water. You burn a bunch of coal. All of the heat from that coal burning is put through a boiler, and you generate steam, and you push that steam through a steam turbine like this, and you generate power. So over the years, there have been significant amount of technology improvements, even with steam turbine cycles. So I'll show you some of the efficiency improvements here. If you look at this chart kind of shows you, CO2 emissions, versus power plant efficiency, and you have percent reduction of CO2 on this side. So the initial coal power plants, these were in this range, that was the subcritical type of power plants, where they operated at roughly around 36-37% efficiency. So what does that mean? So that means that only about 30% of the energy that was released by the coal could be converted into actual electrical power, right? So over the years there have been significant advancements in terms of the steam turbine design, the materials used in the plants, which allowed the use of much higher steam pressures and temperatures. And that's where you kind of come into this ultra supercritical power plant range. So you'll see there's a significant increase in power plant efficiency. So you're talking about, say, 8 or 9% efficiency over, this side of the bar. Now, 8 or 9% may not sound like a lot, but for every percent in efficiency, you're probably saving or not emitting millions of tons of CO2 per year. So that is a significant chunk of CO2 that is reduced through these improvements. So that's kind of where steam power plants or coal power plants have evolved over the years. Now, the next topic really is that over the years we now moved to natural gas, and what are the main drivers for that? Obviously, emissions, being the main thing. If you look at the amount of CO2 emitted between coal and natural gas in order to get the same amount of heat output, you'll see that natural gas actually emits about half the amount of CO2. So that was a very strong reason to go to natural gas. So what's happened with natural gas power plants? So natural gas power plants essentially run, with a simple cycle gas turbine power plant. So this again, in simple terms, what this is that you compress air and then you pass it through a combustion chamber where your natural gas is then burned. You generate a lot of heat, and then you take all of that hot mixture and then you basically pass it through a gas turbine like this, and you generate electrical power. Now, just like steam turbines, there have been significant improvements in the technology with gas turbines as well, in order to improve their efficiency. So here's a chart of how the efficiency of gas turbines have evolved over the years. So if you look at starting in the 1970s, a typical gas turbine power plant efficiency was roughly somewhere around 30%. And over the years, there have been significant increases in efficiency with advanced materials, advanced coatings, other technology improvements. And this is kind of where we are right now with the latest and greatest, the J-class gas turbines, operating roughly around the mid-40s percent efficiencies. So again, if you look at it, a 15% increase in efficiency, over a 30 to 40 year period, that's a significant chunk of CO2 reduction in effect. So that is natural gas gas turbine power plants. Now, again, we still want to continue improving our efficiencies because this is not enough. So what was the next thing that came up? Combined cycle power plants. So the idea simply is that what if we took a gas turbine cycle and a steam turbine cycle and combined them? Can we get more out of the same amount of fuel? The answer is yes. So the idea is that a gas turbine, typically when it runs by itself, it still exhausts out of a lot of heat. That's all waste heat in a simple cycle. But what if you took that waste heat and then essentially ran it through another boiler and then generated more steam, and then you ran that steam through a steam turbine? So in effect, you just recovered more power out of that cycle. So you just improved the efficiency of your power plant. So by the way, the combined cycle power plants running on natural gas are I guess represent the majority of natural gas power plants in the US now. So here's what happened to the efficiency. If you look at it, over the like I said, the J series gas turbine working in conjunction with a steam turbine, you could actually achieve almost a 65% thermal efficiency in a power plant. So that again is a significant jump over both a a steam cycle and a gas turbine cycle. So this is kind of where we are today. That the most efficient plants are operating roughly around this number. So now we still need to improve, right? Because we are still burning natural gas, we are still emitting CO2, although less amount now. So what do we do next? So hydrogen comes into the picture. Now everybody knows when you burn hydrogen, you get zero CO2, right? So the idea has been thrown out that what if we could burn hydrogen in these gas turbines, right? And so this is what a lot of turbine manufacturers like Siemens, GE, Mitsubishi, they're all pursuing today. So this chart over here kind of shows you the hydrogen capability of a gas turbine. So as we currently stand, all of these heavy industrial gas turbines, these numbers by the way are Siemens model numbers, but regardless, the gas turbines today can burn up to 30% hydrogen in the mix, which essentially reduces your carbon dioxide emissions. The ultimate target is that we want to burn 100% hydrogen, right? So now it's not as easy as it may sound, just switching over a fuel from natural gas to hydrogen, because hydrogen burns very differently than natural gas. So there are a lot of engineering challenges associated with burning hydrogen in the gas turbine. So there's a lot of changes to the combustion system within the turbine needs to take place to efficiently burn hydrogen. Yep.
Like a closed system where they would use the emissions as part of like a recycling of power.
Repeat the question. I'm sorry. For the live stream. I'm sorry.
What about like a closed system where you would use the emissions and take the emissions to help run the turbine? Instead of having emissions, have it closed.
Right. So that's a good question. If you look at just a simple gas turbine cycle, you put out some heat in emissions, like you're saying. But if you run it back through the gas turbine, the thing is that you don't have the same temperature and pressure to really drive the turbine efficiently. So the turbine is it's a very custom designed machine in a way, where you're designing certain stages of blades to expand gas at a certain temperature and pressure. So yeah, sure, I mean you could maybe get something out of it if you run it back through the turbine, but not the full extent. So to your question, there are other systems out there where the waste heat is actually used for other purposes, like say like a cogeneration or an industrial plant that needs heat for its process. That waste heat would be used there, and in a way you're improving the efficiency overall, because you just did more with the same amount of fuel.
Because it's being recycled back through. There's no carbon emission if it's closed.
Well, so yeah, I mean you can only recycle it so many times, right? So you need to eventually burn new fuel again, right? So in order to get the maximum power out of your turbine, because that's really what you're going to get you the highest temperature and pressure. So yeah.
Yeah, where's the hydrogen come from? I mean, it takes energy to liberate it from water.
Yeah.
I'm just asking, where does the hydrogen come from?
I'm sorry.
Yeah, that's a good question, and I'm going to move into that soon here. I just quickly wanted to show you a lot of the manufacturers today have their own roadmaps. This, for example, is Siemens Roadmap shows that by 2030s, I would say the target is to reach 100% hydrogen combustion in heavy gas turbines. So a lot of work is going on in the industry today. We just aren't there yet. So so we've kind of tackled the question of actually running the turbines on hydrogen. So here's your question about how do we produce all of this hydrogen. Is if you talk about replacing all of the natural gas that we are using in the US with hydrogen, you're going to need a lot of hydrogen. So how are we going to do that? So here's I've shown you two types, essentially what's currently being called in industry as green hydrogen and blue hydrogen. And what that really is it, for green hydrogen, it means that I guess to back up a bit, in order to generate hydrogen, typically you would, do either an electrolysis process, you're splitting water into hydrogen and oxygen, or there are other methods like steam reforming, where you, from natural gas, you extract hydrogen using steam. So green hydrogen essentially is that the power needed to run the electrolysis process comes from, again, a renewable source. Whereas for blue hydrogen, like, you still have the natural gas, which is the carbon emitting part of it. So that's why it's not your ideal scenario. But regardless, so there's a lot of work going on in developing these industrial scale electrolyzers for generating green hydrogen. Now, so like I said, in terms of generating large quantities of hydrogen, we are going to need huge plants, and this kind of shows you what's going on in the industry right now. Company called Plug Power, they already have green hydrogen plants in work or in construction in these locations. Plan to have 500 tons per year of liquid green hydrogen by 2025. Companies like Energix, they announced plans to build the largest green hydrogen plant in the world in Brazil, 1.3 billion pounds per year. So there are several projects underway around the world that are putting these plants for generating H2. There are, in terms of costs, we are still not quite where we want to be. Hydrogen production in the targets are to reach about $1 or $2 per kilogram by 2030. This is the level where the industry feels like hydrogen can really compete with all of the other fuels out there. So we've kind of addressed, the production side of hydrogen. Now the next question is, how do we transport all of this hydrogen? So one of the possibilities is, we have these, hundreds and thousands of miles of natural gas pipelines in the US already. Can we use these pipelines to transport hydrogen? So again, it's not a simple switch, putting hydrogen in the same pipeline as natural gas. There are, some technical challenges associated with it. For example, hydrogen makes certain types of metal brittle. That's called hydrogen embrittlement. So you cannot, pass hydrogen in certain types of steels, it will just corrode it or eat it up. There's other challenges with hydrogen in terms of the volumetric flows, because hydrogen is a very it's a low density gas, so the equipment that's working in the pipelines needs to operate differently now to pass the same amount of energy through the pipeline. So all of those challenges are being worked on right now. There are research projects going on where they are slowly starting to bump up the amount of hydrogen that's being mixed in the pipeline, and evaluating the results. So that's kind of the aspects of using hydrogen. So as you can see, we are still not quite there where we, in terms of the infrastructure. So we need to find something that we can leverage immediately, which will help us reduce our carbon footprint. So I'm kind of deviating more a little bit towards fuels now. I'll come back to the generation side in a few slides. So I wanted to talk about sustainable fuels or carbon neutral fuels. So what are these fuels, right? So these are your fuels that you're familiar with, like kerosene, ammonia, natural gas, except that they are produced in such a way that the amount of carbon dioxide that is emitted by burning that fuel, the same amount of carbon dioxide is actually absorbed while making that fuel, and that's why they're called carbon neutral fuels. So this is a solution that we can implement soon before we get to hydrogen. So here's an example, e-kerosene. So this I guess CO2 neutral kerosene is being produced for the aviation industry, which, as we know, is one of the highest emitters of CO2. So how is this made, right? So carbon dioxide from the atmosphere is captured. The carbon monoxide is taken from that, and then you have green hydrogen again from a electrolyzer. Those two are used in this Fischer-Tropsch synthesis process, and that essentially gives you your synthetic or e-kerosene. So this is just an example of how a renewable or carbon neutral fuel could be produced. So recently the first commercial plant was made operational in Germany, and you might have read in the news that several airlines have actually already conducted their first demonstration flights using such e-kerosene. So again, we're making progress even with sustainable fuels. These are small steps, but we are still making progress towards reducing our carbon emissions. Now I'd like to speak briefly about nuclear power generation. So nuclear power by itself, by the nature of the process, is essentially a carbon-free process, right? The fission reaction doesn't produce CO2. So nuclear power is a way to reach your carbon net zero goals. So increasing the amount of nuclear power generation is a way you could achieve that. Now, so even in nuclear power generation, right, you use the steam cycle just like your coal power plants. So any benefits that were achieved through efficiency improvements in the steam cycle also apply to nuclear power generation. So regardless of CO2 emissions, you still want your nuclear plants to operate more efficiently. But the challenge with nuclear has not been so much the CO2, because there is no CO2, but it's been more the other aspects of it, in terms of the costs of building power plants, the timelines, all of the regulatory hurdles, right? So the trend has been lately to move away from large nuclear power plants and start thinking and designing small reactors. They're called small modular reactors, which are roughly or less than 300 megawatt. I guess the idea is that you can have much smaller plants that cost much less than these $1 billion large plants, and can be built in a much more realistic time frame. So there are companies like NewScale, which recently or last year it got its design approval from the Nuclear Energy Commission for their SMR design. So there's again a lot of work going on in nuclear, and it's like I said, there's a lot of other challenges associated with nuclear that kind of slow down development in that area. Again, there's other advanced reactor technologies, using different types of cooling mediums that are in the works. So again, there's no shortage of innovation on that side either. So I guess then now moving into renewable power generation, right? So obviously everybody is familiar with solar, wind, those have been around for a while. But what I'd like to show is like what are the developments in those areas, what's been going on in those. So before that, I'd like to kind of put things into perspective as far as how much renewable generation do we need. So if you look at the amount of natural gas power generation and coal power generation, so if you add those up, roughly somewhere around 800 million kilowatts of power that would need to be produced by renewables if you wanted to go 100% renewable, right? And that's a significant chunk of power. So it's going to take a very aggressive scaling up of our renewable power plants to really get us there. So so then along those lines, so what's happening with wind energy, right? So again, we are just like steam turbines, gas turbines, we want to leverage improvements in the design of the wind turbine itself to get us more power. So if you look at how wind turbines have evolved over the years, we initially started off, say in the 90s with land-based wind turbines producing only about half a megawatt. Over the years, because of developments in design, the materials, manufacturing techniques of wind turbines, we were able to make these bigger and bigger and bigger. And this is roughly where we are right now. If you look at the scale, these turbines are taller than the Eiffel Tower right now. But we are not putting them on land. That's the most important part of this trend, is that mostly all wind developments now, large scale wind, is happening offshore, because we can put such large turbines in the water. All of these developments are occurring there. So if you look at the power output, you went from half a megawatt to almost 15 megawatts, and that's a huge improvement. If you had to produce that much power, using these small turbines, you would have a lot more turbines that you would need, and that means a lot more land space that you would need. Yep.
Ask your question again, I'm sorry? What can those large turbines power? Or
yeah, so this is nothing but a different type of power generation, right? So the large turbines out in the sea, they will generate power, and all of that power is then transmitted through cables to land, and that's where it gets distributed again, just like any other power plant.
you're asking what can you use them to, what can you use them to power? I mean, basically, it's another power generation, just like a coal plant or a natural. You know, it's not specific to any particular.
Right, right. Is that what you were asking, or something else?
Yeah, how many homes can they run?
Oh, okay, okay. I don't know off the top of my head like what 15 megawatts of power. Yeah, I don't want to put any wrong numbers out there, but typically like when you're talking about megawatt scales, you're talking about like thousands of homes. So yeah.
You're asking what the building is on the right.
Yeah, that's an interesting question. This doesn't look like it's. Is it the Dubai Tower?
Maybe the Dubai Power, perhaps. Yeah. Yeah, I don't know.
I know the Khalifa looks a little different, but anyway.
There's another question in the back.
Yeah, a lot of the wind energy and all of the research that's being done for these renewable energies are getting pushed back from the coal and the natural gas giants. So when I got my NICEAG bill, I chose to try doing the renewable energy. It was 2 times the price. Right, they're investing in it, but I'm just saying that I think a lot of the development in renewable energy are receiving pushback from these oil companies because they don't want to be replaced.
Yeah.
It's right down into our government. There's even people in our Senate and our Congress that are protecting these oil companies. And they're keeping us from being able to have renewable energy.
Mm-hmm, mm-hmm. Yeah.
How do you fight that?
Yeah, I think the only way I see is that if you were to implement some sort of like a mechanism to sort of almost tax your carbon emissions, right? So it like carbon tax essentially. That's the only way you would level the playing field. Because even oil and gas, they do get some sort of subsidies, maybe not in the US, but other parts of the world where they're heavily subsidized. So it's not really a level playing field when you compare the cost of wind energy to other types of energy right now. So I agree with you. Yeah, I mean there needs to be more of a regulatory type scenario where carbon sources are taxed, and that makes people then think about or choose renewable energy.
Look at the oil spill that just happened in California. The entire beach was covered with oil.
Yep.
Okay, there's no consequences for these companies for ruining our environment. And at the same time, they're monopolizing it and keeping new things from developing.
Yep.
It's just, it's not right.
Yep, I hear you. Okay, so I guess here's another example here. This is GE's Haliade X or 10, as they call it. This is currently the largest wind turbine in production. Produces about 12 megawatts of power, one turbine. And here's some scale. The total diameter is 722 feet. That's huge. So you just think about the manufacturing, the engineering that kind of goes into making these huge rotor blades. Even transportation, like transporting these blades on roads, it takes special vehicles, special permissions to transport these. There's more work being done. Siemens Gamesa, they're testing a prototype for 14 megawatts, one turbine. So they continue to get bigger and produce more power. So that's kind of what's happening with wind energy. And here's, I guess, a New York perspective on wind energy. So you might have heard recently, New York State awarded certain contracts, called Empire Wind and Sunrise Wind. These are essentially contracts to develop offshore wind off the coast of New York and New Jersey. They are projected to have 2,500 megawatt capacity in combination with those. So there's a lot of activity going on in the offshore industry, not just New York. I've heard states like Virginia, Massachusetts, similarly awarding contracts for offshore wind. So a lot of capacity is going to come online in the next few years. Okay, so let's talk about solar. So what's going on with solar energy? So again, from a technology perspective, the focus has been to keep improving the efficiency of your solar cells or solar panels, right? So this kind of gives you or shows you, where we've come from the beginning. In the 1960s, your PV cells were, roughly about 14% efficient. So only 14% of the energy that was incident on the panel was converted into electricity, right? So that's a very low amount. We needed to keep improving. So through the years, through improvement in the materials used in the solar panels mainly, we're kind of almost touching 45% efficiency with solar panels. This makes a huge difference. Although solar doesn't use any fuel per se, it's all free sun. Where this efficiency comes in is that if you have a more efficient panel, you need less of a surface area to generate the same amount of power. So that means you're not putting up huge fields of solar. You need less of a land footprint to get the same amount of solar energy. So that's kind of on the efficiency side. There are other aspects to solar where there's actively there are a lot of active R&D projects exploring floating solar, which essentially means you put solar panels on a body of water, in the oceans where you have a lot of free space, in reservoirs and dams where you don't necessarily use that surface area. So some of those investigations are currently ongoing. There's something called hybrid plants. I'll get into this a little later when it's more relevant. So here was that the full picture from the trivia question. So this is your concentrated solar power plant with thousands of mirrors surrounding it, and they're all focusing the solar sun's energy onto this point in the tower. And here's where typically a fluid would absorb all of that energy, and it would then essentially transfer that to either a water cycle where you generate steam and then again generate power from a steam turbine. So just to give you a rough idea, plants like this can now generate anywhere from 200 to 400 megawatts of power. So there's again a lot of development going on with large-scale solar power. Now, are we doing on time? Okay. All right. So energy storage. This is a very important topic in the transition to clean energy, and I'll show you why it is. So here's a chart of from California. This is on the y-axis. You see power or net load versus the time of the day. So California, as you know, has a lot of solar installations already in place, right? So here's what happens. Early in the morning, your solar is not quite producing power. but you have your other sources producing power, which are your like your base load sources, like your thermal power plants. Then what happens is as the sun comes up, you start to produce a lot of solar energy, but at certain times of the day, your demand actually goes down in the middle of the day, and then as the day comes to a close, more towards the night, your demand goes up, but your solar power has essentially gone down after sunset. So this is typically referred to as a duck curve in the industry. So what's happening here? There's a lot of variability, that you see here, and the risk in such a scenario is that when say in the evening time where your solar is not producing enough power, your thermal power generation now needs to pick up the slack or the load, right? So if you look at this, it's saying that a 13,000 megawatt ramp is needed in 3 hours. So in order to meet the demand from the grid, your gas turbines, steam turbines need to ramp up so quickly in order to meet demand. And what that does is it essentially has a very damaging effect on the turbines, because you're suddenly bringing them up in temperature and pressure, and that really affects the metal, the components in the turbine, and you're essentially reducing the life of the turbine. So such a scenario actually decreases the life of your base load power generation. So that's one reason why you need to store energy during this middle period, so that your base load doesn't have to ramp up so hard. Now the next reason, curtailment. What is curtailment? So again, a scenario from California. So curtailment essentially means that the grid operator is telling the power generator to stop producing power or don't supply us power. And why is that happening? Because when you look at this trend in the late 2020s, 2021, there was a lot of solar installation in California. It was in the summertime, in the middle of the day, it was generating so much power that the grid didn't actually need that much power. So the system operators were telling the operators, no, we don't want 300,000 megawatt hours of power. You keep it, because no one's going to pay for it. And that's just a waste of energy, right? I mean, that you have all of this available energy, but you have nowhere to store it. So that's the second main reason why you need energy storage. And we're not talking about just your small batteries. We need grid scale energy storage. That means storing energy that's enough for a town or an entire city. So what does that look like? Well, the first thing you can do is just pile on your batteries. Just make huge battery banks that can store power. So here's an example. This is currently the largest battery energy storage system in California. It has a capacity of 300 megawatts or 1200 megawatt hour of energy storage. So this is essentially a huge stack of lithium-ion batteries that can provide 300 megawatts on demand for 4 hours at a time. So this is one option, right? Now the problem, there are some issues with lithium-ion batteries. There are some pros, there are some cons. The cons being that lithium-ion batteries, as you start scaling them up in number, the cost goes up exponentially. The other drawback is that lithium-ion batteries cannot be recycled, not recycled, I meant cycled. So up and down every day, up and down every day. That's how the grid, demands power, right? So you can only get a certain limited number of cycles out of a typical lithium-ion battery before it degrades. So what's needed is a better solution to address this grid scale storage. So that's where the concept of long duration energy storage has come up. And what this essentially means is that any technology that can offer us 8+ hours of grid scale storage without the drawbacks of lithium ion batteries. All right, so here's a couple of charts that it shows you the storage time essentially on the y-axis versus the capacity of the storage. So we are talking about a requirement of days or months even at a very high level of storage. So we need technologies that are listed here. There's a lot of technologies that are currently being worked on and investigated, but the one most familiar to you might be the hydro. Hydro or hydropower is essentially a type of energy storage, right? You have millions of gallons of water that you lift up in a reservoir and then you release when you need it, and the capacity is essentially determined by the capacity of the reservoir, how much water can be stored, right? So but there are other types of or other technologies out there that that can offer even better solutions in terms of more duration of storage as well as high power output. So where these can help is where you have scenarios where there's extreme weather. Yeah, sorry.
The question was, how often do you have to replace the batteries with lithium ion?
Right. So lithium ion, there's they're limited to, forget the exact number. It's probably less than 100,000 cycles, but I'm not exactly sure right now. But once you pass those number of cycles, the performance of the battery degrades significantly. So now you have to replace those. And imagine replacing all that entire stack of batteries, right? So that's kind of where the drawbacks come in. So yeah, I was talking about events like extreme weather, like what just happened in Texas, right? If your main base load or other sources of generation go down for days, a system like this could essentially support the grid during that time. So that's where some of these technologies could help. So here's that other example from the trivia. So you were right, this was a gravity-based long duration energy storage system by a company called Energy Vault. And the concept is really simple, right? You use gravity essentially to store energy, and the way they do it is that they have blocks of concrete essentially that they would lift up in a tower, and then using the potential energy of those, when energy is needed to be released, those blocks would be brought down. That's essentially converted into power. So it's a very simple concept, right? I mean, there's nothing groundbreaking about it, but companies are finally starting to put these kind of things into into production, into reality. So this is just one example. There's a lot of other technologies out there, like pumped thermal storage, compressed air energy storage, liquefied air energy storage, and so on. There are other battery chemistries that are being explored. There are flow batteries and so on. But the point I want to make is that all this work is going on as we speak. There are several demonstration plants planned in several parts of the world right now that will have these long duration energy storage technologies in work. So that was energy storage. I think the last topic I want to cover is carbon capture and utilization and storage, right? So what is carbon capture? It's essentially capturing the carbon dioxide at the very source of the emissions, and then either storing it somewhere or using it in another process. So that's what this whole concept is about. Now, why do we need carbon capture, right? So there are still a lot of heavy industries, like cement production, for example, right, where just the very process of production produces a lot of CO2, and that it's not easily eliminated. So there are industries like that where you need to be able to capture carbon at the very source so that it doesn't go into the atmosphere. The second good reason is that in reality, all projections for our climate actually say that net zero is not enough, because by net zero you're only not making the problem worse. You're just limiting the amount of new carbon dioxide that's going in the atmosphere. But we already have the carbon dioxide from previous years. So in order to actually reverse this cycle, we need to capture more carbon from the atmosphere and reduce the atmospheric concentration. So that's kind of this chart is kind of showing you the projections through 2050 as far as which industries would actually need such technologies. Like you're saying, the transportation industry, with electrification, hydrogen vehicles, it's expected that they won't need carbon capture, but the heavy industries would. So here's the other trivia example. So what this is a direct air capture system, and what it is it essentially is a set of fans or blowers, sucks air out of the atmosphere, passes that air through certain absorbents, and those absorbents essentially separate out the carbon dioxide from the air. A lot of these direct air carbon capture mechanisms or machines are already in operation in several parts of the world. The previous example that I showed you with the e-kerosene, it actually uses a direct air capture system to get the carbon dioxide for making the e-kerosene. So again, there's a lot of different technologies with carbon capture. I'm just showing you some examples. There are other chemical-based systems and so on. So yeah, so basically this chart here is kind of showing you that the progress we've made with carbon capture. If you look at it in 2020, we already had a significant amount of plants already in operation. There are some in construction and some in development already. So we are making a lot of progress on that front as well. So with that, I think a few takeaways from I guess the talk today is that the energy transition is happening today as we speak. It's not something that's going to happen in the future. All of these technologies are being worked on right now. The other aspect is that there's no single technology that's going to solve this problem. We need all of these different ideas, technologies to really reach our goals. And the third and final takeaway I would say is that reducing carbon footprints or carbon emissions is really everyone's responsibility. We shouldn't really just wait for governments or countries to announce targets and do something about it. Each of us can take a look at what we do every day and see and identify areas for reducing our carbon footprint. So yeah, that's pretty much what I wanted to share today. I've listed some useful resources for anyone who's who wants to learn more about net zero or energy in general. There's a lot of useful information in these locations, so please do feel free to explore. There is a good PBS documentary called Can We Cool the Planet? I would recommend watching that. It's pretty eye-opening. So yeah, that is all from my side. I hope I kind of gave you a good overview of our energy transition and what's going on in the energy industry.
Thank you. If you've got any questions, any other, I'm going to do my Phil Donahue thing. Pardon me, I'm dating myself, so that people on live stream can hear it.
It's not really a question, it's more like a comment. I mean, I know it's great that they have those things to collect the carbon dioxide out of the air, but we need a global initiative to replace the trees that we have cut down, whole forests in the Amazon. The tree is the ultimate carbon, transforms it to the oxygen we breathe.
Mm-hmm.
If we planted more trees and we replaced what we've cut down, we could reverse global warming.
Yep.
That just by doing something environmental,
Mm-hmm.
not even having to use a plant to produce a piece of metal or a blower that's going to suck the carbon dioxide out of the air.
Yep.
It's an environmental problem that we made, and we have the direct ability, because there's thousands of seeds on a tree for a reason. It was designed that way, intelligent design.
Yep.
We have the ability to use our nature to
Mm-hmm.
heal our planet.
Yep.
And we don't need technology to do it.
Well, I think it's a combination of using all the resources and
Yeah, and it's a good point. I mean, trees are the thing that have kept things in balance so far. If it weren't for trees, things would have just spun out of control. They are significant carbon capturing mechanism. Yes, and
Water and trees.
right. But there's a lot of debate going on this, and I saw some recent research on this. We've sort of gotten ourselves into a vicious cycle where the rising global temperatures are causing the trees to actually absorb less carbon dioxide than they would have normally done. So this is kind of a catch-22 situation, right? So obviously, yeah, we should be planting more trees to do it the natural way. The question is it going to be enough? And that's open for debate, really.
Got another question here.
Yeah, you didn't. You had nuclear on some of your graphs, but you didn't really talk about it. Recently, our former governor shut down a nuclear plant in New York, and the folks in Vermont, which you think would be a green state, shut down a nuclear plant and started generating more carbon dioxide as a result. Fusion is always 10 years away from being 10 years away. You want to comment on your take on the whole nuclear waterfront?
Yeah, so with regards to nuclear, the plants that are being shut down, right, this was technology that was designed 40, 50 years ago. And it's kind of unfortunate that even though there's new technology out there that is much safer than these existing plants, because of the few accidents that have occurred, that seems to take more precedence above the actual technology itself. That's where the whole the public opinion, the regulatory mechanisms, that's really what's blocking the progress of nuclear. It's not to say that the accidents are minor. When things go bad, they go bad really bad, right? But then there's the newer technologies aren't being given enough of an opportunity to showcase that they are safer or better or more efficient. So again, I think it's a lot of like public opinion and policy that's kind of driving the shutting down of these nuclears. Yeah, I mean it's kind of unfortunate.
I think it's also my understanding that the current nuclear plants are only designed to last a certain amount of time. They actually have to be shut down. That they at some point actually cannot continue to operate. and so they're sort of planned after so many years to be shut down. So I think that may be part of also what's going on, and maybe the newer technology that can either look for longer duration or find some other mechanism so that it physically just can continue to last longer. But again, the safety issue always is a big
yeah, that's a good point. I mean, there's certain components in the nuclear plant, you cannot use them beyond a certain time. Obviously things like turbines could be upgraded to newer technology. But as far as the reactors are concerned, all of those components, I'm not really sure how long they can be stretched in terms of their life.
Right. Plus, also the fuel only lasts so long, and then it has to be stored, in a facility that nobody's going to go into for whatever the half-life, half a million years or something like that. So.
Right. The fuel storage is also a big question and problem with the industry. So, yep.
Let me just see if there's anything out in the live stream for questions. Linda did say great presentation, well done, but no questions. So anyway, if you have any further questions, I think we'll be able to ask them directly. Sure. Unfortunately, the skies are not helpful for us tonight here, so you'll have to come back another time. And although, I was going to say, I think pretty much everybody here has looked through a telescope, so that's the one rule I have is before you leave here, you have to look through a telescope. But anyway, so thank you much. I really appreciate your time and information. And next week we have Professor Bruce Oldfield that's going to talk about the geology of New York State and sort of the rocks and minerals that can be found around here. And so if you've got a rock that you want to know what it is, bring it up, and Professor Oldfield will tell you about it. Thanks.